Leah here from LeahForSci.com, and in this video we're going to look at the reaction mechanism for acetals, hemiacetals, ketals, and hemiketals. In the last video, we introduced the acetal and ketal concept along with a trick and shortcut to help you easily identify reactants and products. A few things before we look at the mechanism. These are all reversible and can happen under acidic conditions ideally or non-acidic conditions. We're going to focus on the acid-catalyzed reaction because it's most common to come up in your class and it's the better, faster reaction. This reaction is typically catalyzed by hydrochloric acid or para-toluene sulfonic acid. Phew, that's a mouthful. Don't worry about the acid, just recognize that the acid will dissociate to give us an H+ in solution, which means if your reaction happens in an alcohol like methanol, the methanol will pick up that H+. You can simply show your alcohol with 2 hydrogens and a positive charge as the acid, or even just show H+, recognizing that it came from an acid catalyst. The second thing to keep in mind is why this reaction happens. Carbonyls are reactive because of their resonance. If you're not familiar, you can review in the tutorial link below. This happens because the pi bond between carbon and oxygen can resonate up to that oxygen atom to give us a molecule that has carbon single bound to oxygen, the 2 lone pairs we saw initially on oxygen, and another lone pair from the resonance. A quick formal charge calculation tells us that oxygen has a -1 and carbon with its incomplete octet has a charge of +1. We're not going to show this, we're simply going to recognize that the resonance hybrid is a result of these two, which means we have the resonance going up and down between carbon and oxygen with a partial negative charge on oxygen and partial positive on carbon. This is critical to remember. The partial negative makes this oxygen more reactive than a standard alcohol oxygen, and the partial positive makes this carbon susceptible to attack by something negative or partially negative. We'll use simple molecules for this mechanism, starting with aldehyde reacting in an acid-catalyzed ethanol solution. Pay close attention to the colors so that you can identify where each atom came from, where the electrons came from, and ultimately be able to follow along. Now I'm warning you, it looks like a long, tedious, scary mechanism. So 2 things to remember before we start. 1, pay attention to the why. When trying to figure out the next step, I like to ask myself this question. What's the most positive in solution right now? What's the most negative in solution right now? And how do those 2 interact? Because typically the charges will be attacked or neutralized going into the next step. The second thing is to notice the pattern. This reaction is intense, but it's very similar to many of the other carbonyl reactions that you see in organic chemistry. So once you learn one and understand the pattern, you can apply this to all the other crazy reactions you learn later on. Let's begin. What is the most negative in solution right now? Well, this is an acidic solution. That means we're typically not going to see negative charges. In fact, it's my pet peeve when students write a positive and a negative oxygen in the same solution, because typically they don't play nicely together, they're going to attack. In an acid-catalyzed solution, the most negative species will be a neutral electronegative atom, for example, oxygen with 2 electron pairs. What is the most positive? Well, obviously the proton, floating around in solution with a positive charge, or sitting on alcohol as ROH2+, again with a positive charge. Here's the question. Which oxygen attacks the proton? Is it the alcohol or is it the carbonyl oxygen? And before you argue about the alcohol, yes, we have a lot more alcohol in solution, so technically it is the alcohol. But once that happens and exists as a positive oxygen, it's still going to be a question of what is ultimately the stronger negative oxygen, and that would be the carbonyl. Why? Because this oxygen, remember, has a partial negative charge from resonance. Due to the pi bond, it's got a much greater electron density. So even though this is most common because of the volume, we have way more alcohol because it's the solvent in solution. To start this mechanism, it's ultimately going to be the carbonyl oxygen electrons that reach for that proton. Think of this as the activation step. We activated the carbonyl making it even more reactive to attack. How did that happen? We already saw the resonance has a partial positive charge on carbon and a partial negative on oxygen. This oxygen was greedy. It reached for a positive hydrogen atom and got its wish, but now it has regrets because oxygen now has 3 bonds, 1 lone pair, and a formal charge of +1. Oxygen, as an electronegative atom, is unhappy with that positive charge and starts to pull on the electrons between itself and carbon even more to try to make up for that positive charge. The more oxygen pulls electrons away from carbon, the more partially positive that carbon, the more susceptible it is to attack. That's what I mean by an activated carbonyl. Well, what is the most negative in solution right now? A neutral oxygen atom, for example, our solvent. What is the most positive? Well, this partially positive carbon, because oxygen is hogging all the electrons. So we show one of the solvent molecules attacking the carbonyl carbon to form a new bond between oxygen and carbon. This puts too many bonds on carbon, so it breaks the bond between carbon and oxygen, collapsing the pi electrons onto the oxygen atom, just like oxygen wanted. Our intermediate is called a TCAI, a tetrahedral carbonyl addition intermediate, because the carbon is now bound to 4 different atoms and is a tetrahedron because of the sp3 hybridization. Some professors will refer to the TCAI. Make sure you know what they're talking about. The green oxygen still has the hydrogen atom and 1 lone pair, giving it a formal charge of +1. What is the most positive in solution? The hydrogen atom. Remember, positive oxygens don't get attacked. They're greedy. They pull electrons from something nearby, something that's attached, making that atom partially positive. So even though the charge sits on oxygen, it's hydrogen that's most partially positive and ultimately hydrogen that gets attacked. I want to remind you that even though my habit is to draw single-headed arrows, these are actually reversible. So what is most positive? This hydrogen. What is most negative? An alcohol in solution. What does that do? Well, another alcohol in solution with its oxygen will reach for that hydrogen, collapsing the electrons back onto oxygen, giving me a neutral intermediate. What's most negative? Oxygens in our intermediate. What's most positive? More protons floating around in solution. At this point, you should recognize that we have a hemiacetal because carbon with the hydrogen is bound to a blue oxygen that's an OH and a green oxygen that's an OR. This is where a lot of students get confused. If I have protons floating around in solution, we can show it as an H+ or sitting on alcohol. Which oxygen grabs it? Is it the OR group or the OH? And the answer is technically both. Remember, it's a reversible reaction. If the OR grabs it, we simply go back to the previous step where we have a protonated OR, and that doesn't help us because we can go back and forth a million times. So instead, we'll only show the step that takes us forward in our reaction, showing the OH grabbing the hydrogen. Again, it's not that only one oxygen grabs the hydrogen, but rather, we don't want to waste time going back and forth. We simply want to show the next step in the forward direction. This gives us a blue oxygen with 1 lone pair, 2 hydrogen atoms, and a positive charge. You should remember from previous reactions that protonating an OH turns it into a good leaving group because OH2+ is not very happy, but a water molecule in solution will be much happier. Many professors will show it simply breaking away, but what you want to show is electrons from the neutral oxygen collapsing down. Remember, oxygen is greedy, it never knows when to quit, and when it's neutral, it'll keep trying to grab more. When oxygen electrons collapse down, carbon would have 5 bonds, which can't happen, so we use that attack to kick out the water molecule by breaking the bond between carbon and oxygen. This gives us an intermediate that now has 2 bonds between the green oxygen and carbon, for a total of 3 bonds, 1 lone pair, and a positive charge on oxygen, along with a side product of OH2, which is a neutral water molecule in solution, 1 lone pair from the initial oxygen pair, and 1 lone pair from the bond that broke away from carbon-oxygen. Water is gone, But we're not done. We have a regretful oxygen atom with a positive charge pulling on the bond between itself and carbon, once again making that carbonyl carbon very partially positive. What is most negative in solution? Another alcohol molecule, which will show attacking the carbonyl with a lone pair and breaking the bond between carbon and oxygen to collapse the electrons onto the oxygen atom. The intermediate now has a green neutral OR group and a purple protonated OR group from the incoming alcohol. The purple oxygen has a lone pair and a positive charge, making the purple hydrogen most reactive, making it susceptible to attack by another oxygen in solution. For the final step, some professors will show the conjugate base from your initial acid catalyst grabbing the hydrogen. Ultimately, it doesn't matter. It's something basic in solution that deprotonates the hydrogen, giving the electrons back to that oxygen atom to give us our final neutral product. We have the carbon chain with the hydrogen. We have a green neutral OR group and a purple neutral OR group. Our final product is an acetal, which has the carbon chain with the hydrogen, and attached to the carbon we have two neutral OR groups, the green alcohol from the first attack and the purple from the second. In solution, you'll notice we have a side product in the final step, which is the protonated alcohol, which is the alcohol we use to deprotonate the final oxygen. This is important because the rule of a catalyst is that it doesn't get destroyed in the reaction. A catalyst can get used but has to be regenerated. We started the reaction with a protonated alcohol as the acid catalyst, picking up a proton from solution. And we end the reaction with a protonated alcohol holding that hydrogen, which if we dissociate would just be that proton once again floating around in solution. And again, as a reminder, these are reversible steps. Be sure to join me in the next video where we'll look at the mechanism for a cyclic acetal protecting group. You can find this entire video series along with the acetal practice quiz first by giving this video a thumbs up, then checking the link in the description or visiting my website leahforsci.com/acetal.